Hey guys, so we need to finish out the gases portion of this unit. Now your gases packet had almost everything in it because a lot of the gases stuff is review from last year. The only one that was missing from your gases packet, and you may have noticed it, was Dalton's law of partial pressures. We did learn it last year. It was a very simple, straightforward law that simply had the equation, PT is equal to P1 plus P2 plus P3. You can see this on your paper. And it just kind of continues on depending on how many parts you had to your mixture. And this is that one that we talked about where if we had a whole bunch of gases separate from each other and they were exerting a certain amount of pressure on their container, if you transferred them all into the same container together and kept the volume constant, that the pressure in the new container would simply just be the addition of all of the pressures of the individual gases. So if you have a mixture of gases, all you have to do is add up their partial pressures and you can figure out what the total pressure is in the container. The only key that you have to remember with that is that your units do have to match. If they don't match, you need to convert them. So like if my P1 was in ATM and my P2 was in millimeters of mercury, I would need to convert into the same unit to be able to do that calculation. But it's pretty straightforward equation, I think. Not a lot of different, solving like you have like in PivNerd over PivNerd. It's pretty much just plug into those variables and then solve. So let's go ahead and try an example problem. So you see there on your notes it says a mixture of gases contains nitrogen gas with a pressure of 453 millimeters of mercury, oxygen with a pressure of 1.2 atm. So notice right away we have an issue with units. The first one was in millimeters of mercury, the second one is an atm, and then the third one is also an atm, and they want to know the total pressure of the mixture. Now they want the final answer, you notice here, in millimeters of mercury. So you can solve this really however you want in terms of getting things into like units. But since we're ultimately going to be in millimeters of mercury, I'm going to choose to convert both of these ATM values I have into millimeters of mercury. So if you'll go ahead and do that, take this one and this one and do your conversions and get them both into millimeters of mercury. You can pause while you do that. Okay, so you should end up with these values. So the O2's millimeters of mercury is 919.6 and the argon's is 2.622. Then now, so we have all three of them. We already had one in millimeters of mercury. That was the nitrogen value. So we can go ahead and write our equation. So we have three different gases. So we're going to have oxygen gas, argon, and nitrogen. And we have all of them in the same unit. So I'm going to simply plug in those values. You can see my work here. I have them all plugged in. I have my equation, which you always have to show. I have my plugged in version of the equation. I've shown my unrounded, which you don't have to do if you don't want to, and then my rounded to correct sig figs answer. Okay, so we have 1,380 millimeters of mercury. So if you're given individual pressures of different gases in a mixture, make sure all their units match up and then add them together. Now that's the way we learned Dalton's law last year. The reason why we're doing this as a separate lesson is because we are going to add on to it a little bit. The way we're going to add on to it is that there's two other ways to figure out your pressures with a mixture as well, sort of dependent on what your scenario is. This scenario, this is your only option. They've given you the individual pressures, make sure they all match and add them. But what you're going to see, if you look at the next example problem, skip down below these equations, you'll see that they have not given you pressures. They've given you moles. And they're talking about temperature, they're talking about volume, yet they're going to ask you for the total pressure and they're going to ask you for the partial pressures. So how are we going to figure out all of that information? Well, it's going to go back to PivNerd. If you look up at your equations that you have there, you have regular old PivNerd right here. Now, it might not look like regular old PivNerd because there's a T right here and a T right here, but those T's are standing for total. And that's what you've always done with PivNerd, is you've been calculating the total pressure using the total moles of gas. We are going to allow ourselves to use that equation for specific parts of a mixture as well, and using it the exact same way we've always used it. But instead of saying total pressure comes from total moles, what we're going to be looking at is individual gases. So for example, let's say you had a mixture, and that's what I'm showing here. It's the mixture of O2 and N2. I can take my total moles for both of these, plug them in over here, and solve for total pressure. Yeah, that's great. But I can also look at O2 as one thing and N2 as another. If I take just my moles of O2, see that right here, and I plug it into this equation using the temperature, the R, and the volume, I can figure out just the pressure of O2. Now notice it's only the moles and the pressure that have the O2 on them, because the volume is the volume of the container, the temperature is the temperature of the container, and R is a constant. So I would be able to figure out the individual pressure for O2 this way. And same thing with N2. If I look just at the moles in the container of N2, then I would be able to figure out the pressure of just the N2. So we can use PivNert for more than what we've been using it for. We can actually use it to break down the parts of a mixture. Let me show you how this looks in a real problem. If you go to the next problem here. So you'll see we have three things in our problem. We have moles of N2 that are given. We have O2 in our mixture, and they gave us the moles of that. And then we have moles of F2. So we have three parts to our mixture. Notice they've told us the temperature, which we're going to need to put in Kelvin, always in Kelvin, and the volume, which is in liters. Okay, so the first question says, what is the total pressure in the container? So total pressure in the container, with all the volume and temperature measurements, we know we're going to be using PivNert. But if they want total pressure, then we need to be using total moles. So we're going to use the PivNert equation with the totals, which is the one you've always used. And we're going to plug in our information. So we know our volume was 2. We got that from there. We know our 4.5 is our mole value. So how did we get this mole value? Let's look at that. So the moles for N2 was 2.5. The moles for O2 was 1.5. And the moles for F2 was 0.5. And if you add all that up, you end up with a total moles of 4.5. Okay, so that's where that came from. Of course, you know your R is always what R is, and then our temperature was converted from there. So I just took three separate pieces of information that they gave us in the problem and combined it to figure out total moles. And then I solved. So my total pressure in this container of the O2, N2, and F2 combined is going to be 55 atm. Okay, so that's pretty much what we did before. It's new in that in old problems, I would have just told you that the gas's mole value was 4.5, and you would have been able to use that. In this case, you had to actually add it up yourself. Also, they don't have to give these to you in moles. Remember, they could have given them to you in grams, and then you would have to convert them. So keep in mind that that is a possibility of a slight extension of this problem. Now take a look at B. B wants us to figure out just N2. So if we're talking just N2, then all we care about are the moles from the N2, which is 2.5 moles. We're going to ignore all the other gases. We don't care about any of the other ones. So we're going to write our equation. We're going to plug in our information. So this time, again, we still have the same 2.0, so this part's still the same. We still have R, and we still have our temperature. But what's different is that right there, how many moles we have. The first problem we did total moles. That one was total moles. Now we're looking only at the moles of N2. So if you calculate that, you end up with 31 atms is coming from the N2. That's the pressure of the N2. So it's a total of 55. 35 of it's coming from N2, which makes sense because N2 had the most moles. The most moles is going to exert the most pressure. So it kind of all fits in with the ideas we've been studying. All right, why don't you go ahead and try C and see how you do on it. Go ahead and pause the video. All right, so for C, you should have written your equation like such. Again, we're going to have consistency with this part, and this part. The only thing that changed was that you only had 1.5 moles of O2. So you're going to calculate your P of O2 as 18 atm. Go ahead and try D. Pause the video. All right, for D, you should have, let's see here, sorry. Okay, so you have your pressure of your F2 in your equation and your moles of F2, so that's the only part that's different. These parts all the same, and we solve and we get an F2 pressure of 6.1 atm. Now some of you may have, when you were doing this last problem, you may have said, well, how about I just use PT equals P1 plus P2 plus P3, because you had already calculated total pressure, you knew the pressure of the first gas and the pressure of the second gas, and you could have solved for the pressure of the third. That's okay to do. It's a completely viable last step, and so if you did that, that's fine. You would get a slightly different answer because of sig figs, but I'm okay with that. So long as you show your work, I can see that you're getting one answer because you use this as your equation, or you're getting a different answer because you use this. Either way, absolutely works. So whatever way you're most comfortable with is fine with me. Okay. All right, so that's the Pivnert way. So if you're given temperatures and volumes and mole values or gram values, you need to use the Pivnert way to do the problem. If you're given just the pressures right off the bat, then that's the lovely way of just adding them up. Now we have a third situation that we're going to encounter. If you take a look at this problem, sorry for this up here, I don't want to confuse you. So let's take a look at this problem. What you see is that they've given us grams of our substance, okay, and then they've given you grams of another substance, and we know we can convert grams to moles. So that's essentially a mole value that they've given us. We just have to do the conversion. They've given us the total pressure, and then they're asking us the partial pressure. But if you go to try to use Pivnert in this problem, you're in trouble because you don't have volumes and you don't have temperatures. So if you're given information similar to that last problem, but with no volumes or pressure. So up at the top of your paper, write, when I'm missing volume and temperature. When I'm missing volume and temperature. So if you are missing volume and temperature, we can't use the equation that we've already learned how to use. We have to use a different equation. And you can see it there on your paper. I don't have any space here. Okay, here you go. So the equation is the partial pressure, so the pressure of A, meaning whatever substance it is that you're figuring out, is going to be equal to the moles of that individual substance over the total moles times the total pressure. Okay, so again, you might label these. This right here is moles of individual gas, or individual part, whatever you're trying to find. And then down here is total moles. And then right here is total pressure. And then here is partial pressure of individual gas. Ooh, sorry. This right here is actually called a mole fraction. Mole fraction meaning part of the moles over the total moles. And that allows us to be able to do our calculation. If you see in some books, they actually write this equation as the pressure of the individual gas is equal to X, capital X, that's the mole fraction symbol, times total pressure. But I like to look at it like this equation because that substitutes in what mole fraction actually is. And it's more applicable for us to be looking at it from that point of view. So the partial pressure will be the moles of your individual gas over the total moles times the total pressure. Notice this equation doesn't have volume or temperature in it. So it allows you to use moles information with pressure information to be able to figure out another pressure value. So let's go ahead and try a problem so you can see how this works. That's what we had over here. Now, you may have noticed before I erased it, this is kind of an ugly compound. It's kind of big, long. I don't want to have to keep writing it over and over again in my work, and you can always do something like this. So what I'm going to do is I'm going to make myself a note that I'm going to substitute C2H2BrClF3 with the letter A, just kind of like a variable, so that I'm not having to continuously write that problem or that formula over and over and over again. So first job is going to be to convert both of these given values into moles. We don't want grams, we want moles. So pause the video and do that. All right, so our mole value for our A compound should be 0.075988. Please make sure you didn't overround. This is an intermediate answer. We need to keep it unrounded. Also check your molar mass. Should have had 197.4. For O2, the mole value is 0.73438 moles. So we have both of our mole values that we need. And in the problem, they had told us right here, the total pressure was 855. Now, because there's no R in this equation, we don't have to be in ATM. We can be in whatever pressure unit we want. So we're going to go ahead and leave it in millimeters of mercury just to not do an extra conversion because it doesn't specify what it needs to be in. So next step is going to be to write out our equation. Now, once you have your equation written, you're going to plug into your equation. So remember, this was the moles of the individual gas. So in this problem, they asked us to figure out the partial pressure of each gas. So I started with calculating the partial pressure of my A. You can see I have it labeled here as A. So I'm trying to figure out what A's pressure is. So that was the moles of A. It was A's moles. Now down here was total moles. And the way you get total moles was by adding the moles of A plus the moles of O2. And that gave us this 0.81 number. And then over here at 855 came from the total pressure that was told to me in the problem. Now I'm going to divide all of that in my calculator, and I find out that the pressure of A is 80.2 millimeters of mercury. Now we're going to do the same thing, but we're going to do it for the other substance in this problem, which was O2. So notice now I have O2s written here. Total moles is going to stay the same. Total pressure is going to stay the same. So if you compare the work for this problem and the problem we just did, the only difference is right here. This is the moles of O2. So you're going to plug all of that in. You're going to solve and find out that the partial pressure from the O2 was significantly higher because there were significantly more moles of O2 than your A compound. And then if they asked you to, verify your answer, add up 775 and 80.2, and you will find that you get an answer very close, because of rounding, to 855 millimeters of mercury. So you might as well always double check your work as well. So 3 equations, 3 different ideas, all relating around the same concept of Dalton's law. So you'll either be given, and it'll probably be a good idea to write these down in your notes, and you can kind of pause and rewind, but if you need to. The first one is you're given all pressures, and you're going to add them together. Just make sure the units match. That's the first type of problem. Second type of problem, you have volumes, you have temperatures, you have moles. You're going to use Pivnert for that. It can either be Pivnert with the totals plugged in or individual gases, okay? But you're going to use Pivnert when you're given moles and volume and temperature. If you are given moles, and remember moles can be grams because you can always convert that, but if you're given moles and pressure only, then you're going to want to be using this last equation that we have here, this equation that uses the mole fraction. And so that's really your 3 different categories of partial pressure problems. All of these problems relate to what do we do when we have a mixture of gases.